Assalamualaikum and good day everyone. Welcome to the OTC Asia live session. Okay, my name is Johaidi Jaafar from Malaysia Petroleum Management Petronas, and I will be the moderator for today's University R&D showcase. In this session, I will welcome Mr. Chew Yu from the University of Nottingham, Malaysia, to share a presentation on process simulation and optimization for acid gas removal system in natural gas processing. Okay, Mr. Chew is the final year student of chemical engineering at University of Nottingham, Malaysia. This work is part of his final year project together with his supervisor, Professor IR Dr. Dominic Fu, along with industrial collaborator Dr. Zulfan Adiputra from Petronas. Okay, managing acid gas in our producing fields and plants is becoming more critical as the time of abundant sweet gas is almost over. For safety reasons and eventually in assuring the economics of any project, the gas that passes through our facilities and plants must be below the allowable limit to avoid any incidences or long-lasting impact to the people, asset, environment, and reputation. Throughout the presentation, I encourage the audience to pay close attention and think of any question and submit them in the online chat. We will be addressing these questions during the live Q&A session afterwards. Okay, without further delays, I will invite Mr. Chew Yu to the stage to begin his presentation. Good luck.
Thanks to everyone. I would like to deliver on project namely process simulation and optimization for acid gas removal system in natural gas processing for OTC showcase. From figure 1, we can see that the carbon dioxide emissions for natural gas is the lowest among the various fossil fuels with the value of 600 grams CO2 per kilowatt. This emission intensity is 23.2% lower than the oil and 57.4% lower than the coal. Hence, the combustion of natural gas emits fewer greenhouse gases into the atmosphere. In the drive towards sustainable development, natural gases plays more important role in energy security during carbon dioxide abatement. However, acid gases such as hydrogen sulfide and carbon dioxide are abundant in natural gas. These gases have an effect in terms of safety, economic, and environmental. Therefore, chemical adsorption is commonly used for the removal of these acid gases. Although this is a mature technology, it has several drawbacks to consider. The problem statement of acid gas removal system can be formulated as follows. A large circulation rate of alkanoamide is required to remove the hydrogen sulfide and carbon dioxide to the specification limit, which will result in high operating costs. The carbon dioxide loading capacity of alkanoamide will be affected by the pressure of adsorber column and temperature of solvent. This affects the energy consumption in the process. Emission of carbon dioxide into the atmosphere will incur carbon dioxide penalty. Therefore, the main aims of the problem are to minimize energy consumption and minimize operating costs of the process by using process simulation and regression-based optimization. It is important to evaluate the optimal operating parameters of the sweetening process. The methodology of this work can be classified into 5 steps. In step 1, literature reviews have been carried out to determine the parameters that affected the acid gas content and operating costs. Aspen HYSYS version 11 was used to imitate the process behavior of the acid gas removal system. After that, several scenario analyses were used to gather data while the data generated were exported to Microsoft Excel. With the data, closure of trend in the graph was obtained by performing curve fitting function. In step 3, the relationship of each operating parameter with carbon dioxide content in sweet gas was evaluated through the built-in regression method in Excel. Next, from the obtained equations, they were utilized to develop surrogate models to predict carbon dioxide content in sweet gas and energy consumption of the acid gas removal system. These surrogate models were then used in Lingo for optimization to accomplish an explicit objective, which is maximizing profit, in this case, for each fulfilling all constraints. Lastly, the result from the soft model was validated in the simulation model and justified to ensure the solution was robust. The base case simulation in HYSYS as shown in figure 2 has a typical process flow diagram of the sweetening process found in acid gas removal system. For this plant data, they used MDA as the solvent and air instead of water in the cooler. The flash gas discharge was sent to flash system. Next, for step 2, according to figure 3, the larger the lean MDA recirculation rate, the lower carbon dioxide content in sweet gas. The operational cost for utilities was contributed by the reboiler, heater, air cooler, and pump. carbon dioxide penalty cost was considered into the operational cost as the carbon dioxide was discharged into the atmosphere after exhaustion and combustion of unrecovered natural gas in the flare system. This applies to Figure 4 and Figure 5, which will be discussed later. In this scenario analysis, the increase in lean MDA recirculation rate improves the efficiency of the exhaustion, but this gives rise to a high amount of energy required for the utilities. From Figure 4, it can be seen that the concentration of carbon dioxide decreases when the pressure increases. A similar trend for operating cost was obtained in varying absorber pressure as mentioned in Figure 3. Lastly, based on Figure 5, the composition of carbon dioxide in sweet gas show an inversely proportional relationship with the lean MDA temperature, which is in line with the Henry's law. For the total operating cost, an opposite trend was acquired. When the lean MDA temperature decreased, the amount of energy required for the air cooler to cool down the MDA solution increases. Therefore, the operational cost increases. Since the independent variables mentioned in Figure 3 to Figure 5 have effects on the carbon dioxide content in the sweet gas, a further investigation has been carried out to identify the relationships between them. According to Figure 6, the results show that these three independent parameters are integrated in acid gas removal system. To establish an optimization framework, an objective function should be identified followed by some constraint to restrict the model. For this case, the sales of sweet gas Rs were not a constant because it relied on the other independent variables. Therefore, the objective function of this optimization framework was to maximize the profit. There is one constraint to satisfy the model. The CO2 contained in the sweet gas X CO2 must fulfill the maximum sales gas requirement, which is 1 mole%. To assure the effective optimization framework, the independent variables should be varied within their limits as shown in Table 1. The flow rates of sweet gas, energy stream required for the utilities such as reboiler, heater, air cooler, and pump, as well as the flow rates of carbon dioxide were modeled as a function of other independent variables discussed beforehand. The relationships among each independent variables were deduced from the result generated in the process simulation model. Correlations between them were then established using data fitting and regression function in the Microsoft Excel and summarized in Table 2. According to Table 3, the value of carbon dioxide content in sweet gas obtained in lingo that is less than 1.2% is accepted, although the percentage difference is larger than 1%. This is because the absolute difference for the value is relatively small. Besides, the percentage difference for the profit earned for acid gas removal system per day between two sets of findings is unique and is less than 1%. Therefore, it is agreed that the optimization framework which uses a mathematical model is robust and compatible with the simulation results obtained using Aspen HYSYS. Nevertheless, the accuracy of the model decreases when the carbon dioxide content exceeds 1.2%. This is due to the absence of the data beyond 1.2% of carbon dioxide content in sweet gas in Figure 6, which will be used to derive the mathematical relationship. Moreover, the HYSYS optimizer converged models to ensure local optimal will result in unreliable or inaccurate outcomes. On the other hand, global solver in lingo optimization will generate global optimal solutions to maximize the profit for acid gas removal. Hence, lingo optimization is essential and more robust than the built-in optimizer in HYSYS. Table 4 summarizes the value of the independent variables after performing optimization in lingo. Next, it can be observed that in Table 5, the profit for the plant increases 23.25%. This is compensated by the increase in carbon dioxide content and hydrogen sulfide content. Note, generally, there will be a dehydration unit and hydrocarbon recovery unit to ensure the sweet gas is dry before selling it. However, the operational costs involved in these units are not considered because profit improvement in terms of percentage should be the same for the same mass flows. Instead of conducting single objective optimization, two objectives conflicting with each other were identified because trade-offs were required between the objectives. Maximizing the profit of acid gas removal system while minimizing carbon dioxide content in sweet gas lead to the formation of multi-objective optimization. Steady decreases in the improvement in profit of acid gas removal system is noted when the carbon dioxide content in sweet gas increases by a value of 0.001. This is attributed to the lower additional energy required to remove carbon dioxide from sweet gas. However, as represented by small change in gradient, the improvement in profit of acid gas removal system is the smallest when increasing carbon dioxide content in sweet gas from 0.011 to 0.012. With the constraint for carbon dioxide content at least smaller than 0.01, the optimal solution selected has the profit of 0.98 million per day for acid gas removal system. In conclusion, this work utilizes an optimization framework that employs an integrated simulation optimization technique to reduce the energy usage and operating costs for acid gas removal. Accurate and reliable simulations are connected to a rigorous optimization algorithm allowing the global optimal operating conditions to be determined. Comparison between the results of LINGO and Aspen HYSYS suggested that the framework is robust and resilient when the carbon dioxide content is lower than 1.2 mole%. With the carbon dioxide content in sweet gas of 1 mole% and the hydrogen sulfide content is maintained below the 4 ppmv limit, the profit of acid gas removal system can be improved by 23.3% compared to the base case. In future work, it will be beneficial to reduce the step size and increase the range of the independent variables during the generation of results. Additional data obtained can improve the accuracy, reliability, and validity of the optimization model. More objective functions can be considered into Pareto analysis, so plant engineer can choose the most appropriate solution from Pareto optimal set based on the industrial needs. Lastly, the surrogate models can be deployed to the engineers on the site as a modeling tool instead of HYSYS, as people on site do not normally have access to license or work remotely in a platform. Thank you.
Okay, thank you, Chu, for the presentation. It was an excellent study that you are doing there. Okay, to the audience, we welcome questions to enhance better your understanding and probably also to help Chu and his team to enhance his study. Okay, I have a few questions already here. So I'll go to the first one. Chu, ready for this one? In any research, it's quite important to have reliable data and abundance of data, I can say. So from your study, what data do you wish to have more or made available to improve the accuracy of your analysis?
Okay, so in the future world, right, it will be beneficial to reduce the step size and also increase the range of the independent variables during the generation of the results using the Aspen HYSYS. So if we are going to have like the additional data obtained, it can improve the accuracy, reliability, and reliability of the optimization model. In terms of the independent variables, all the main factors are covered in the equations in the optimization model. However, I'm not sure that whether the incorporation of terms with two factors such as flow rate multiplied by pressure, such as FR multiplied by PA, or temperature multiplied by the pressure, TR multiplied by PA, which will improve the accuracy of the model. Yeah, I think that's it for me for this.
Okay, thank you for the answer there. Hopefully, it can satisfy some of the queries from the audience. Okay, we have the second question here. How much does it differ in terms of operating costs when you're using air instead of water as the cooling medium in the plant?
Based on the plant data for the cost for the operating for the air blower contributes more than 50% to the operational cost for this plant data. As water is easily accessible in Malaysia, using water as the cooling medium will decrease the cost compared to electricity to operate the air blower. Since this is an existing plant, additional capital costs will incur to change from air blower to water cooler. Therefore, a proper financial analysis should be carried out to determine whether is it worth to replace the air blower. Okay, that's it.
Okay. So, yeah. So that means there's a lot more cost to be considered besides the operating cost, but also maybe the investment that is needed to maybe change. Okay. All right. Okay. Let's see. We have the next question here. Okay. What are the major factors should we consider in balancing between the solvent effectiveness and operating costs during the sweetening process?
Okay, so give me a second. Can you repeat the question? Repeat the question again.
Okay, sorry. What are the major factors should we consider in balancing between the solvent effectiveness and operating costs during the sweetening process?
So first of all, the quality and quantity of the acid gas to be removed is one of the factor. So there will be 4 scenarios over this. First of all, there will be like the first scenario will be like the carbon dioxide removal when this is the only contaminant for the acid gas removal. Also, the second scenario will be like the hydrogen sulfide removal when this is the only contaminant of the gas. The third scenario will be a simultaneous removal of the carbon dioxide and hydrogen sulfide. The fourth scenario will be the selective removal of hydrogen sulfide when both carbon dioxide and hydrogen sulfide are present in the gas. So, for example, MDEA has higher selectivity in hydrogen sulfide removal than MEA or DEA. So MDA is usually used in the scenarios for simultaneous removal of both carbon dioxide and hydrogen sulfide. Also, the second factor will be corrosion rates. For instance, MEA has the highest corrosion rates compared to other MEs, particularly when the acid gas loading is high or the concentration of MEA surpasses 30%. And also, the third factors will be the degradation of alkylamines. If the amines degrade easily, more solvents need to be added up, which will increase the cost. I think this will be the three main factors for this. This will be the three main factors in balancing between the solvent effectiveness. Yeah, that's
Okay,
it.
okay. Definitely there are separate costs that need to be evaluated for each of the factors that
Yeah.
we need to consider. Uh, for, I'm pretty sure there will be follow-up questions to this one, and I encourage the audience to bring that in right now or soon after. I'm pretty sure Chu will be more than happy to answer or entertain these questions. Okay, let's see if we have more questions here. Okay, this one, we stick with the MDA. Yeah? How do we improve the effectiveness of MDA absorbent at a higher concentration of acid gas? Maybe 20% of CO2? In your study here, I think you are doing at 1.5%, isn't it? Yeah, yeah. Because 20% is something that we are in the business is looking at to manage better now. All right, go ahead.
Yeah, because for my current case study, right, it will be around 10%, 10% plus, which is less than 20%. So if the concentration of acid gas will be higher than 20%, it will be effective for the MDA as a solvent in this situation. So as a solution, instead of replacing the MDA for the solvent using for the acid gas removal, we can use, instead of replacing the MDA with the MEA or other alkylamines, different schemes or technologies can be applied. So for example, right, we can use the dual absorber scheme where the where a second absorber column can be installed to meet the requirement instead of using the one column, which is shown in my project. Also, we can use a hybrid scheme where a membrane unit is installed before the absorber column for bulk removal of CO2. So basically, if it's for offshore, the company need to determine whether which scheme they want to use because of the acid gas concentration that will be used instead of using one absorber, because usually for the offshore there will be the acid gas will be higher than 20%. So they need to decide whether which scheme they need to follow. Yeah, I think that's it for me.
Yeah, okay. For acid gas concentration of lower than 20%, the normal practice now is to blend the gas with the sweet gas available. And the sweet gas availability is becoming less now. So, yeah, we need to find a solution fast actually to deal with gas source with higher CO2 or any acid gas concentration. Okay, let's see if we have more questions here. We have a bit of time here. Okay, let's see. Okay, the next one. Okay, this one may be a bit general here. More countries in the world right now are imposing penalty for any CO2 emission. So some of the penalties can be high, and some of them might not be too much for some of the countries or companies. How do we balance between self-discipline and penalty, which, as I mentioned just now, could be not deterrent enough for the companies or maybe countries to impose? Yeah, go ahead.
Okay. So based on my opinion, right, as the carbon dioxide emissions penalty cost is not a mandatory law in Malaysia yet, so the reputation or the corporate image will be the key to balance the self-discipline and also the penalty. So in the recent years, companies seek to enhance and protect their corporate image by demonstrating their respect for the environment and by taking actions towards the objective. Some of the most accomplished corporate social responsibility practitioners of today originally began reporting their actions in reducing carbon dioxide emission as they saw transparency of information as the only way to rebuild the consumer confidence. So for the one of the example about the corporate image, right? For the BP, for the Gulf of Mexico, the Deepwater Horizon rig, the blowout in April 2010, where they accidentally killed 10 people and released a total nearly of 5 million barrels of oil into the sea. So technically, the shares reduced. The image will be the image of the company reduced, and also the share also reduced. So this shows that the corporate image is quite important for this case. Yeah, I think that's
Okay,
it for
okay.
me.
Yeah, I agree 100% with you on the corporate image, on the reputation of the companies or even the countries. Whenever any incident happens, any mishaps, because they don't maybe put enough, say, measures to manage this acid gas and to manage I mean, the operations that could actually impact the people, the asset, environment, and as you mentioned just now, maybe company reputation. Okay, we have more questions here. Let me see. Okay, if there's no more question, I think we can wrap up the session. Okay. Uh, okay. Thank you, Chu, for addressing all the questions that we have so far. Hopefully, there will be more questions coming up later on as we will have this presentation available in various platforms for the audience to view and actually ask more questions. Okay, thank you everyone for joining today's session and for interacting with us. It was a great honor for me to moderate the session and to learn more on how we continuously finding ways to optimize our process while keeping the environment safe. The questions and discussion points posted will be available for Chu and his team to further enhance their research. Plenty of information for us to digest and be used for our own studies and evaluation. Hope the audience will find some benefit from this discussion and have a better view and strategy on how to manage acid gas. Okay, last and not least, best of luck to Chu and his team. Thank you.
Thank you.
Okay, so hopefully this has been a good sharing and looking forward to see you again in the upcoming OTC Asia live sessions. Thank you.
Thank you.